Good afternoon, everyone. My name is Ben Marsh, and I'm going to be talking a little bit about tools and infrastructure as it applies to Epic. So a little bit of background. I've been at Epic for about 6 years now, and I'm lead on the developer tools team. We own a lot of the little tools that many of you probably use every day, things like Unreal Build Tool, Automation Tool, Unreal Game Sync, Unreal Front End, lots of things beginning with U, Crash Reporter, things like that. And various parts of the game development process associated with that. So things like we do lots of things to do with Perforce, we own the packaging pipeline, we do lots of automated testing, own the unit testing framework and so on. And we also own a lot of services that we use inside the company. The biggest one of which is Epic's internal build farm. That means that we're constantly under siege from games like Fortnite or Spy-Jinx or Battle Breakers, as well as being responsible for shipping quarterly releases of the engine and special projects that we do for GDC and SIGGRAPH and so on. We're a really small team. There's just 4 people and myself, and that means that we really need to think carefully about the sort of work that we take on. We're doing a lot of firefighting every day, and we really need to focus on optimizing for maintainability. There is a lot of potential for us to positively impact everything that people in the company are doing, though. And the fact that we own so many tools means that we can do a lot to make things integrate together really well. We can solve problems in a really holistic way. Historically, we've kept those sort of things to ourselves. We tend to think about engine releases as being just a drop of the code base, and then it's at your discretion how you choose to use that and deploy it. That's something that I'd like us to change, and over time we're going to open up more and more of our internal tools so that hopefully other people can use them as well. It kind of feels like everybody's trying to solve the same sort of problems, so anything that we can do to share the work that we've done, the more that you can take advantage of it. So in 4.24, there's a bunch of previously internal tools that we'll be sharing, and I'm going to talk a little bit about some of them today. So quick agenda on what sort of things I'm going to talk about. First, I'm going to talk about source control. For us, that's Perforce. So how we manage branches. We have a bunch of live products that we're working on, and we're shipping engine releases regularly. So how we manage branches, how we get everybody working together. Then I'm going to talk about our build system, how we set that up. And finally, I'm going to talk a bit about the feedback loop, how we get notifications for things that go wrong to developers, how we kind of oil the machine and help things keep on working smoothly. So first of all, source control. For engine branches, we kind of adopt a branching structure really similar to the kind of best practices recommendation from Perforce. We have a kind of topology like that where we have release streams at the top where we're trying to stabilize releases, bug fixes are going into there. Then we have our main line, and then right at the bottom we have our development streams. That's where all the feature work is going on. The kind of rule of thumb is that you only put really crucial, smaller bits of work into the release stream. So it tends to be bug fixes and things like that. And they are generally really safe to merge down into all the streams below it. Whereas all of the development streams, there's lots of crazy new features going in and stuff like that. You really want to get QA to check things thoroughly before you try and copy anything up. We want to try and optimize for stability in that whole process. So we kind of have as many development streams as we can get away with. We want to make sure that people who are developing features are doing so with a stable build of the engine plus just their own changes. And that system works really well for the engine. It works really well for source code because you can merge it. For games where we have lots of assets being changed constantly, the same sort of thing isn't as easy. So there we have more of a tension between stability. We still want to have release streams so that we can stabilize things for releases which are about to go out, or even hot fixes for our live releases. We've got a tension between the stability for that and the desire to separate out and give people space to be able to sort of work quickly. We don't want to hold people up. We don't want to impose too many restrictions on people checking in new content and things like that. So we still have this kind of structure of releases, of branches, but we want to minimize them as little as possible, as much as possible, so that there is few places that people can create conflicts. the way that we originally started doing that, we had an engineer, a very unlucky engineer, who would, at the end of every day, have to try and merge down the content of release branches into streams below it. And it didn't, needless to say, it didn't work very well at all. First of all, there'd be a lot of conflicts. And it's difficult to sort of come up with a default policy for what the resolution for that would be. Regardless of which way you resolve the conflict, whether you accept in the source branch or the target branch, you're going to leave things in an inconsistent state compared to what either person has designed them. Either stream has designed it. So you're going to break things by doing that. If you want to resolve those conflicts, it usually involves somebody having to redo work. And that usually has to be the original author. The engineer who's doing the merges doesn't really understand what the changes that were made, not helped a lot by unhelpful change list comments and so on. But it needs to be done by somebody who understands the various systems and stuff like that. They can understand how to reapply the original change. So in order to get past that, we decided to set up a system which would automatically merge down changes from release branches one at a time. That has a lot of advantages because first of all, we do everything in order, one at a time, so it means we can really localize what it is that's causing the problem. But it also helps us to figure out accountability. It helps us to figure out who it should be that needs to resolve it. If somebody has made a change, then they get information, they get feedback straight away telling them that they've caused a problem. It's fresh in their mind what they've been doing. They know exactly what they need to do to replicate it in a different branch. And the tool that we made to do that is called Robot Merge. This is a screenshot of it. As you can see, we've put all that Fortnite money into font licensing for the logo up there. It basically supports lots of different branch hierarchies, like pathways that it can merge down. And at any one point, any one of those can be blocked by an asset that's created a conflict. You can see tabs along the top showing all the different streams that we have for the engine team, or, well, some of them anyway. There's a little red icon next to them showing the ones that do have a conflict. And there's a little graph down there showing the behavior that Robot Merge has. It's configured there to automatically merge down everything in UE4 main into the dev build stream. So the source code for Robot Merge is included for the first time in UE4.24. It's got lots of other useful features inside it as well. Whenever it does encounter a conflict that needs resolving, it'll send you an email and ping you on Slack. And it also has this functionality so that you can ask it to create a shell for you on request. So in Slack, it shows up with like a bunch of buttons that you can sort of say how you want to resolve it, like accept the source, accept the target, or you can say just create a shell for me in one of my workspaces. You can also override it so that rather than doing the default behavior of just merging down, you can say, like, I'm in the main branch, I've just discovered a bug, it's a really trivial bug, and I want to merge it up to a release branch by putting hashtag robomerge release 0.1, and you'll change this description when you submit it. Robomerge will take that and merge it up for you. You can also tell it to avoid creating conflicts that, I'm just going to make a hack in a release branch right now. I don't want you to merge it anywhere, so you can tell it to just ignore that change or just do null merge down. Better than creating conflicts and trying to optimize the process of resolving them is to avoid creating conflicts in the first place. So we have functionality in the content browser, which the same way as that you can see when somebody else has an asset already checked out, you can ask it to scan other branches as well and warn you about changes that have gone into those branches as well. So on the left-hand side there, you can see that it's got a message saying that somebody else already has that asset checked out in a different branch. So if I can keep on working with it, then I'm likely to cause a conflict. And on the right, you can see that somebody has already changed that asset in another branch. So if I submit it, it knows it's going to be merged down. It's giving me a warning that that I'm going to create a conflict that way as well. This isn't just like icons in the content browser either. If you actually try to go through the operation, it'll give you a dialog box that'll pop up, give you more information about exactly what's going to cause the problem. It's a little bit rough to configure that stuff because it's configured through code. We do that for a reason. That's so that for our live games, then when we create new streams, we create new streams every couple of weeks or so. Whenever we do that, we're going to automatically set up RoboMerge anyway. So there's already a RoboMerge config file somewhere which is telling it exactly how it should merge changes between the streams. So we can just have the config, the editor query exactly the same file to figure out how to set it up. This example here just shows you how to set it up manually, but yeah, we usually set it up from the robot merge config file. The next thing I'm going to talk about is the build system. First of all, I want to walk through what a typical build process looks like for a UE4 game. First thing we have to do, this particular example is a client-server game, so first thing we want to do is compile our client and server. And before we can do that, we need to generate all of the, we need to run Unreal Header tool to generate all of the reflection metadata for it. Normally when you compile a client or a server, Unreal Build tool is going to automatically compile Unreal Header tool for you, but since we're doing it on the build system, we want to do it as optimally as possible. Let's split that out and show it as a separate step. So first we compile Unreal Header tool, and then we can compile our client and server, and then we get to the point where we want to cook the client and server data. Before we can do that, we have to compile the editor, and we can do the cook, and then we can bring all those steps together and stage the client and server. And it's only after that that we can start running tests or publish our build or whatever we want to do. That's a really small example of what sort of things you'd usually have to do in a typical game. First of all, you'd usually have, for Fortnite, for example, we have 5 or 6 different platforms that we're shipping on, so you can imagine that duplicated across to the side. But there's also lots of other special things that you always end up needing to do. So for iOS, for example, you might want to take a build and upload it to TestFlight. Or for our desktop platforms, we might want to take a build and upload it to our launcher. Or we might want to run some special stuff for anti-cheat reasons or some auditing or something like that. We're also in a situation where we're not just doing this for one game. Internally at Epic, we're doing a bunch of different games at the same time, and we have things like the engine releases and the Unreal Studio releases, and all the samples that we want to do for all of those things. That means that it's really difficult for us to scale and maintain one build script that's going to do all of those things. We started thinking about what an ideal build system would have for us. Started thinking about what we can do in order to sort of optimize that process of making scripts for different builds, how we can set up our build processes and make it scale better. We came up with a list of requirements. So first of all, we want to be able to share steps between targets. So if we're building like a Mac client and an iOS client, say, they're both going to require an Unreal Header tool to be built. They're both going to require the editor to be built so we can do a cook. We want to be able to share that stuff between them. We also want to have, be able to, if we've got a giant build process which is containing all of the bells and whistles and everything we could possibly ever build, we want to be able to prune it down to just the things that we care about. So when we discover there's a critical switch bug that's in the wild, we want to be able to sort of prune the graph, the dependency tree down to just building one particular thing. We want to make it really easy to parallelize things. Just in the really simple example that I showed before of what the build process would look like, all the dependencies and stuff like that, there are so many opportunities for parallelism in that we really want to be able to exploit that. And we know that there's going to be lots more of those kind of things that come up in the future. So we want to make it really easy to write something that is going to scale well on the build farm. Part of being able to make it scale well on the build farm is to take artifacts that are produced on one machine and be able to transfer it to another machine. And doing that manually involves an awful lot of boilerplate code. So we want to make that as implicit as possible and make it as easy to write scripts for it. We're also branching all the time. We're always creating new release branches because we're operating a bunch of live products. And we don't want to have to maintain lots of different things on the back end to be able to support that. When we're developing those build scripts for different streams as well, we want to have an area where we can test them before they get propagated everywhere else. We don't want to be able to. We don't want to have to check something in straight away or change something in our source control system, which is instantly going to affect branches which we already know are stable, and there shouldn't be any. They're hardcore lockdown. There should be no changes going into them or anything like that. Finally, because we have a bunch of products that we're shipping, we kind of see that there are a bunch of differences between them, and we don't want to compromise on what any of those products want. So rather than trying to design a kind of Uber pipeline which is going to be perfect for everything, we wanted to be able to like embrace the need for different products to do different things and just make it easy to do that. So we want to build up like a shared library of things that every product can opt into if they want to, but if they want to do something different, then they can. The solution that we came up with for that is a system called BuildGraph. BuildGraph is a kind of makefile-like scripting language that is built in XML. So kind of similar to Ant or MS Build. But from the start, it's designed for parallelism. It's not an afterthought. It's not something that's tacked on. It's not designed for doing your local builds and then like maybe we can have some extensions to it that'll allow it to run on the farm or something like that. It's designed from the start to be efficient when executed in parallel. The fact that it's in XML is, I don't know, XML has its haters. It's kind of very, lots of symbols and stuff like that. But the one really great thing that it has is support from IDEs for schemas. So whenever you're editing it, you'll, in Visual Studio, say, you'll get like IntelliSense and you get autocomplete and all that sort of good stuff. And that's the kind of thing that makes any kind of domain-specific language like live or die. So in a BuildGraph script, we declare a bunch of nodes. They can all have dependencies on each other, similar to how a makefile has dependencies on other targets. Each node is going to execute a sequence of tasks in serial. And the whole thing is implemented inside Automation Tool, which means that it's really easy to extend it by adding new tasks. All you need to do is derive from the custom task class, and you can add something special for your project, and it will be automatically integrated into BuildGraph. You can add it into BuildGraph scripts with kind of like in a really native way. I'm not going to dwell on the syntax for BuildGraph because there are a bunch of examples of it included with UE4, and the documentation for it is pretty good at this point. Yeah, there are a bunch of examples included with the engine. So the script for building the installed engine build itself is included in UE4, as well as a script for Shoot a Game, I think the engine test project, and a few examples showing other bits of the language. The one thing that we can't share at the moment, unfortunately, is how we actually take one of those BuildGraph scripts and distribute it. But I want to talk a little bit about how that process works so that if you want to try and do it yourself, then you can do it. The idea is that, so BuildGraph defines all of the steps that need to execute and the dependencies between them. And then we have a third-party build system which schedules that work. For each step that BuildGraph wants to run, the third-party build system will call back into BuildGraph and execute it. Can be on a different machine and so on. And BuildGraph understands the way that, as part of the BuildGraph script, you've already declared sort of what the dependencies are, which machines, how you want to group together nodes to run on different machines. And so BuildGraph can take care of transferring any artifacts produced by a node and then fetching them back on a different node. Because this concept of sort of grouping together of nodes, which we call agents, because they're grouped together and it understands it, then if you're executing two things on exactly the same agent, then it knows it doesn't have to zip up like 40 gigs worth of content to be able to share it to something else. So it's really efficient. So taking that example on the left-hand side there, that little graph, we've got like node D at the bottom, which depends on C, B, and A, and also D depends on E. And the most efficient way of splitting that up to run on different machines is that A, B, and C can run in sequence on one machine, and then E can run in parallel on a different one. And then right at the end, we have D, which depends on C and D. We tend to want to avoid busy waits on the build farm, partly because we can end up with resource starvation, so that like D would never run. But also, we don't know whether C is going to finish first or E is going to finish first. So we have a separate machine which is going to execute D. So how does that look like when it's actually run on the farm? First of all, we get, like the user goes to the build system and kicks off a job to do something. First thing it's going to do is spin up a machine which is going to sync down the workspace. It's then going to run Automation Tool using the run UAT batch file, and it's going to run the BuildGraph command. Passes the path to the script that you want to execute, and passes D as a target. That means it's going to prune off everything else that's in the graph apart from D, and just figure out the steps which are required to complete it. It also passes the export steps argument. What that's going to do is output a little JSON file which will have a list of all of the steps that need to execute, not the actual commands that need to execute as part of them, just the names of them steps themselves. So A, B, C, D, and E. And it's going to specify the dependencies between them. The idea is that the third-party build system will then pick up that JSON file, and it will be able to create the skeleton of a job which is going to execute that stuff. And it can set up all of these steps and set up all the dependencies between them so that it can then recursively, well, not recursively, it can call back into BuildGraph to actually do the work of building them. So that's what it does. First thing it can do, first thing which doesn't have any dependencies that it can actually execute is A. So we get a machine that spins up, it syncs down the workspace at exactly the same change list number, and it runs BuildGraph again. It passes exactly the same parameters, passes the path to the build script, passes the fact that we're building up to target D, but it also passes the single node A argument. And that means it's only going to execute A. That gives BuildGraph enough context to understand exactly what the pruned version of the graph should look like, but tells it that we just want to build part of it. After we've built A, then we can start executing both nodes B and E. And BuildGraph knows that E is going to execute on a different machine. So it's tracking all of the artifacts that are created when you're building A, and it's going to zip those up and transfer them to a network share somewhere. The network share is passed with another argument to the BuildGraph command. So once that happens, then the third-party build system can spin up another machine, which can then sync down the workspace at exactly the same change list number, and then we run BuildGraph again with the single node E argument. As soon as BuildGraph sees that, it's going to say, oh, okay, so I'm building down to target D, I'm only building E, so that means that all of the artifacts for A already exist somewhere. So it's going to go off to the network share, find the zip file that contains all the artifacts, copy it back over, unzip it, and it's going to create kind of like exactly the same as the workspace would look like if you'd built it locally. After that, back on the original machine that built A, we can carry on building B and C. And then finally, after both of those are finished, we can have another machine that starts up and builds D. So that's kind of like at a high level how we model what our build process looks like. More practically, how we want to implement that stuff. We start thinking about lots of ways to be able to scale everything we're trying to do at the company. We find that on our build system, we have something like 50 branches being built at any one time. It might be more than that. And we've got a farm of about, I think it's about 175, maybe 200 machines, which is a lot, but not a lot when you consider how much we're building and the fact that we're shipping some games on 6 or 7 platforms and so on. One of the things that we found was that the more that we do to try and carve up our build farm to, like we're going to have like 3 machines which are going to build this branch, 3 machines that build this branch, all those requirements, all the demands on it are changing constantly over time. So we want to try and make it so there's like a homogeneous pool of machines that can do all of this work as much as we possibly can do. There's 2 elements to that. First of all, the fact that workspaces are really large and we don't have a lot of disk space. I think in our UE4 branches, the footprint is something like 400 gig. And it's kind of a problem that we could throw money at just by buying insanely expensive, really large hard drives and so on. But like even if you have like a 4 terabyte drive, that's only 8 branches. So it doesn't really scale very well. The other aspect to it is that different branches have different software requirements, especially since we're actually developing the engine ourselves and we're doing the SDK upgrades ourselves, then whenever the console team introduce a new SDK, then that change is going to slowly propagate to all of the other development streams. In general, we want to make sure that our build farm is as efficient as possible. So we want to reduce the amount of setup time before we can do useful work. The whole idea with BuildGraph making it really easy to parallelize things is kind of dependent on the idea that whenever we take a new machine or we want to put it to work actually doing something as part of our BuildGraph, we want to make that setup time as short as possible so that we can get going straight away. And back when we started implementing some of this stuff, it was kind of in the early days of containers and things like that. But it's not an ideal solution for what we're trying to do. First of all, we care about we're trying to make builds that run on Mac, Linux, Windows, and still today, like sort of cross-platform support for containers, especially using native tool chains, isn't great. There's perhaps a possibility of using virtual machine images or something like that, but you still have a problem of having to actually maintain those images and generate them and keep them up to date. And as changes propagate, source code changes propagate down through branches, you have to make sure that we're always using the right VM image for each branch. So we came up with a system which is much more lo-fi than that, but actually works really well for us, which I've written there is lo-fi sandboxing. I don't know why. So the first thing that first sort of problem that we solve is how we're going to manage so many workspaces. The thing that really kills us with managing workspaces is the fact that Perforce is very server-centric in all the operations that it wants to do. We want all of our builds to run from a clean slate, and Perforce's solution to that is, oh, okay, I'll go through every file in the workspace and I'll hash them all. Yeah, that's what I'll do. I'll hash them all, and I'll send all those hashes to the server, and the server will tell me which ones are different or which things it doesn't know about. And that's really inefficient because it doesn't take into account things that we know locally. We know that when we sync down a file that it's going to have a timestamp, and unless we have something that's misbehaving, which we shouldn't, nothing's going to change that timestamp. So as long as we store the timestamps for all the files that we've synced, we can tell whether something's tampered with it. If we have a record of all the files that we've synced, then we also know which things we didn't sync down and which things that we can clean out. So that helps us to quickly convert all of our workspaces back to a pristine state. The other aspect is how we handle lots of different streams. Fast stream switching is a really appealing idea because it means that you can take the current state of a workspace, switch it to a new workspace, a new stream, and just sync down the deltas, just sync down all the differences you need. It's still a very server-centric operation, though. All those deltas have to be pulled from the server. It also kind of has a reputation for not being very reliable if like a stream switch is interrupted and so on. Like, is what you have on your local machine the previous state? Is it the new state? Is it halfway in between? Was there anything lost in transit because you interrupted a sync operation? So what we do instead is to manage that stuff manually. We keep a local cache of all of the files that we need to sync down, which are kind of indexed by the MD5 digest. Perforce is computing the MD5 digest for everything that it stores anyway, so that's a good place to start from. The idea is that when you want to sync down a branch, you can sync it down as a sort of server-side operation only. So you sort of flush the workspace to the new state, and then you can ask the Perforce server, okay, what should the contents of my workspace be? It's going to report back to you a list of files as well as the MD5 digest for all the files that are in that workspace. And then you can go and look up all of the things in the cache to see whether you already have them. If there are any things you don't have, you can force sync them. The other really important thing we do to optimize that whole process is that rather than treating the cache as a kind of a sort of bounded thing that just stores a copy of all the data, we kind of use the cache as a kind of like like a holding depot for all of these files. So whenever we want to set up a workspace, rather than copying stuff from the cache, we just move the files over. If there are two files in the workspace which have the same digest, then we can move the file to the first location, and for the second location, we can just copy it. When we come back to sync a new stream later on, we can integrate it with all the fast workspace cleaning logic. We'll know the MD5 digest for all the things which are already deployed into the workspace. Anything else, if a file isn't needed again, it can move back to the cache. If it's needed and it's in the right place, we can just keep it. So the tool for doing that is another thing that we're including for the first time in 4.24. It's a tool called BuildAgent. The source code for it is under that location there. This is kind of like an example of just some of the command lines you can run with it. First of all, if you want to sync a workspace, you can pass the sync command, pass the base directory you want to sync it to, specify the name of the client. It'll automatically create it if need be, or it'll switch it to the right stream if not, and pass the stream and the changes number you want to sync. Next up, you can clean a workspace by passing the clean command. It already knows what the supposed contents of that thing is because it wrote out a file with all the metadata containing it when you did the original sync. So you just have to pass the base directory and it'll figure it out automatically. The other really useful operation that we have is the populate command. That's kind of designed to prime the cache. So we run it every week on our build farm on a Sunday, I think. And we pass it all of the streams that a machine can service. The idea is that it will sync down all of those streams in order, populating the cache with all of the files needed for it. And it will purge the cache of anything that's no longer referenced. That means that at any point during the next week, if we ever need to build something on a machine, at most it's going to be 6 days out of sync with whatever's already in the cache. The other thing that we have to be able to manage a homogeneous pool of machines is something that we call AutoSDK. AutoSDK is something that we've had for a long time, but haven't documented until now. And it's kind of difficult because we don't have the rights to distribute all the SDKs from different platform vendors. What it is that it's basically a system whereby like at a location in your Perforce depot, you check in all of the SDKs that are required, not just for that branch, but for any branch that you want to service. So there might be like 3 versions of the Android SDK, 10 versions of a PS4 SDK, and so on. Anything that wants to use Auto SDKs can sync down that branch and set the UE SDK's root environment variable to the local directory on your hard drive where it is. And as it's needed, then all of our tools will register and install things from those SDKs. We actually don't tend to have to install an awful lot of things because most SDKs just consist of like a bunch of tool chains and so on. All you need to do is to set a bunch of environment variables and you can use them in place. So that really helps us reduce the setup time. There's no actual setup time apart from setting a few environment variables for a lot of these things. All of the environment variables are generated by batch files, which are checked into directories underneath the AutoSDK root directory. And it has to obey a certain naming convention for those to work. In 424, we've included the batch files that we've written ourselves, as well as instructions for where to place the vendor SDKs and so on, so that you can set it up for yourself. The last thing I'm going to talk about is the feedback loop, how we get information back to devs. In case you haven't seen it before, this is a tool called Unreal GameSync. Unreal GameSync has a kind of interesting history. It's a tool that's designed for syncing down from Perforce. And it came from a time when, well, our build system wasn't anywhere near as efficient as it is now. And we had a long lead time with, the process that we had was that our build system would sync down code, it would compile the editor, it would check in binaries into Perforce, then QA would come and test those binaries. And if it was good, they'd apply a label to it, and then all of our artists could sync it down. And that loop was really, really slow, especially when we were starting out on Fortnite, and there was kind of a sense that the project was stagnating a little bit because artists and, designers and engineers weren't working together very well, because like an engineer would have to, engineer would check in a change, and then you'd have to wait like a day or two for editor binary show up for the designer to use, and they couldn't do any blueprint stuff using it until that point. So we tried out this idea where we would get everybody in the company to sync down from Perforce and compile the editor themselves. Even artists, even designers, everybody would do it. And Unreal GameSync was designed as a front end for that kind of stuff. So everybody could use the same process. You see a list of all of the changes, the same as you might see in P4V or something like that. You can just double click on one of those and it will sync it down and compile it for you, and then launch the editor. Nowadays, Unreal GameSync has a a bunch of functionality into it, so that you can download zip files containing precompiled binaries and use those instead. So we don't still make our artists and designers compile things locally. But one of the big successes that we had with Unreal GameSync was all those green badges you see there on the right-hand side. The idea was that like whenever we get a build system to like run some tests or compile it for different platforms and stuff like that, we can surface the results of those compiles kind of in line with a list of all of the changes that have been checked in. That particular example, that particular screenshot there is cheating a little bit because there's like 6 changes being checked in a day, and like on Fortnite we have 6 changes being checked in a minute. So the build system has had time to catch up and populate all of that stuff, whereas normally it wouldn't. That feedback loop for telling people about build failures, half of the things that we're doing on the build farm aren't to actually generate something, they're to just generate feedback to tell people that their stuff is broken, or to validate everything that's been submitted. We want to catch things as early as possible because we've already set up our branches so that we've got as few branches as possible to avoid creating conflicts, we're kind of forcing a lot of people to work in the same place, and they're kind of like, they're really on top of each other. So if somebody introduces a bug, there's a good chance that they're going to hold somebody else from working for some time until they fixed it. And once a bug's been submitted, it's really easy to have a kind of red-on-red situation where somebody else checks in a bug over the top of it, and they don't notice because the build was already broken to start off with. So we started getting these notifications to people through emails, and we found that, first of all, they were incredibly noisy. Because as the projects got bigger and we wanted to start building things on more and more platforms, adding more and more tests and so on, every one of those would generate a separate email. And we'd run those tests all the time as well. So not only would you get like 10 emails from the first time you broke the build, you get the same thing like a few minutes later as well. And we're also robo-merging all of these changes. So all of the bugs that people are introducing, we're robo-merging down to 3 or 4 streams below it. So then they send emails as well. Even after you've submitted a fix for something, you're still getting like emails for things that people fixed like an hour or 2 ago. The other drawback with emails is that they're kind of difficult. Well, there's no way to update them with more information after the fact. So if we realize that something is the same problem as something happened before, we can't just update to say, oh, and this is also happening on this other platform or in this other branch. We just have to send another email instead. One of the possible solutions to that would be entering bugs, and we use that as well. We have like our QA department entering bugs, and they go into somebody's triage queue, and if we're lucky, they'll triage them once or twice a day, get over to the right person. But they also kind of get lost in the noise. There are so many bugs going around. There are so many things that we have to fix. People are overloaded, and we kind of want to jump the queue and make sure that they're focusing on this thing. So we set out trying to write a system that would solve some of those problems. We kind of called it the build health system. So the goals for it were we want to deduplicate errors between different platforms and tool chains. We want to deduplicate errors which are happening between different streams due to merges. And we want to automate the triage of that stuff. We know how we can, it's really easy for a human to look at 2 like compile errors and say, oh, that's the same thing, it must be the same cause. And so we want to make a machine version of that. We want to automate it. We don't want to have to wait on somebody in QA periodically checking what the state of the build farm is to go in there and enter a bug or figure out who needs to go and fix it. There's also the people side of it. We want to make sure that when somebody is told that they've caused an error, they've introduced an issue, we want them to acknowledge it. We want them to be able to, we want them to let everybody else know that they're working on it, they've seen it. They haven't just walked away from their desk they haven't gone into a meeting or left for the day or something like that. And if they have, if they don't acknowledge that they're taking up the cause of trying to fix this bug, we want to have an escalation path for it. We want to be able to escalate it to their discipline lead, there's somebody more senior on the project, something like that, so that they can find somebody else who's going to fix it quickly. So this is what we made. It's another utility which is built into Unreal GameSync, that being the kind of hub that we have for all of our notifications nowadays. If I've checked in a compile error to plugin style.cpp, it will give me this big obnoxious red notification that will stick in the corner of my screen. And there's no way for me to dismiss that apart from to acknowledge it or to look at more information about it. If the system isn't quite smart enough to figure out that it was me that caused it, then it knows that there's some change between change list n and change list n plus 10 which caused it. So everybody who checked in that range, it'll give a message like that too. That gives me the option to say, oh, okay, yeah, plug install.cpp, yeah, that's probably affected by one of my changes, and take up that bug so that everyone knows that I'm trying to fix it. Or I can just say it's not me. And if everybody says it's not me, then I'll go through the escalation path. If you click on the details button, it'll bring you up with a nice window like that, which will give you a sort of concise description of the error messages that were encountered. Let me see lots of other things, like it has links to the builds that it failed in and so on. You can assign it to other people through that. So if you're one of the people on the escalation path for something, this is a really useful place to come to be able to triage things. There's also a changes tab in that, which is for those people who are doing the escalation stuff, who are triaging those sort of things, super, super useful. You can see at the bottom there the last build that succeeded. At the top, there's the last build that failed. It's highlighting in bold the person who it figured automatically, the automated process figured caused the bug, but it also shows every other change in there as well. And you can use that search box at the bottom to search through all of the descriptions of the changes, all of the files of that changed, that kind of thing. You can put wildcards in there. Makes it really easy to track down who you think caused it. So how does that process work? First of all, we run all of our build steps through BuildGraph. So we have that run uat.bat BuildGraph command at the top there. Rather than just executing that on our build system directly, we use the BuildAgent tool to run it again. There's a command in BuildAgent called run. And what that's going to do is to run this child process, capture all of the standard out, and as it's outputting text, it's going to be running a bunch of regexes over it. And those regexes are designed to pick out things like compile errors. It knows what the syntax of a compile error is. It understands what a multi-line compile error is. It knows what an MSVC compile error looks like, and a Clang compile error and stuff like that. And it can parse out that data, and it will generate a little JSON file, just containing a list of all of the errors and warnings that it detects. It's going to take that JSON file, and it's going to put it on a network share somewhere. And it's going to sit there on the network share, and everything else that runs on our build system as well is also going to populate it with lots of these little JSON files containing all the errors and warnings. Periodically, then, we run a separate job on the build farm. It runs through the BuildAgent tool again. It's called update issues. It's going to go through all of the JSON files that exist on the network share, and it's going to run all that deduplication logic on it. It's going to talk to Perforce. It's going to figure out who's changed which files. Like, if I've got a compile error in this file, then odds are the person who changed it last caused it. So it can figure out all that stuff. It also knows about robomerge as well. So when robomerge automatically merges a change from one branch to another, it puts a special little tag in it saying that this was actually originally change list whatever in whatever stream. So it can trace it back to where the change was originally submitted. So it can deduplicate things that way as well. Using that information, it builds up a kind of local persistent state of all of the issues that it thinks are currently affecting the build farm. That information can then be turned into issues which are uploaded to the Unreal GameSync metadata server, which is the thing that all of the users who are running Unreal GameSync are polling periodically to figure out, like, is there anything that I need to show, and so on. It's got a database attached to it. All of the issues go in there. And all that stuff is polled by all the clients running on different people's computers. All of those users can interact with the issue. They can say, like, it wasn't me, assign it to somebody else, and so on. Just sends things back to the metadata server, it gets updated in the database. This is a really new system for us. It's only been running for like a month or two, but already it's been super useful. And if you're using Unreal GameSync especially, I would really encourage you to give it a go. And yeah, that's it for me.